A very good morning, everyone. I Anam with Anshika and Nasreen are here to present our discrete mathematics presentation on the topic the Hamilton path and circuit. This is the content of our presentation in which we are going to discuss history of Hamilton's path and circuit, its definition, examples, Dirac theorem and Oates theorem, problems based on Hamilton circuit, formula to find the number of unique Hamilton circuits in a graph, and applications of Hamilton circuit. History. The terminology of Hamilton circuit comes from a game called Icosian puzzle invented in 1857 by the Irish mathematician Sir William Rowan Hamilton. It consisted of a wooden dodecahedron, a polyhedron with 12 regular pentagons as faces. The game consisted of a graph in which the vertices represent major cities in Europe. Now, the objective of the game was to find a path that visited each of the 20 vertices exactly once. In honor of Hamilton and his game, a path that uses each vertex of the graph exactly once is known as Hamilton path. If the path ends at the starting vertex, it is called a Hamiltonian circuit. Now, let us see how a Icosian puzzle actually looks like. It consisted of a wooden dodecahedron, a polyhedron with 12 regular pentagons as faces, as shown in figure A, with a peg at each vertex of the dodecahedron string. The 20 vertices of the dodecahedron were labeled with different cities in the world. The object of the puzzle was to start at a city and travel along the edges of the dodecahedron, visiting each of the other 19 cities exactly once and end back at the first city. To solve this puzzle, Hamilton creates an isomorphic graph of it, which is shown in figure B. So this is the solution of Icosian puzzle given by Hamilton. This is a circuit that passes through each vertex exactly once. Now let us move to definition of Hamilton path and circuit. A simple path in a graph that passes through each vertex exactly once is called a Hamilton path, and a simple circuit in a graph G that passes through each vertex exactly once is called a Hamilton circuit. That is the simple path x0, x1 to xn minus 1 to xn in the graph G is equals to VE is a Hamilton path if V is equals to set of x0, x1 to xn minus 1 to xn and xi is not is equals to xj for I greater than equals to 0 less than j and for j less than I greater than I and less than equals to n. And the simple circuit x is equals to 0 to xn to x0 with n greater than 0 is a Hamilton circuit if x0 to x1 to xn minus 1 to xn is a Hamilton path.
Now, let us move on example of Hamilton circuit. First example is graph A, so that Hamilton circuit because their starting point is A and ending point is also A and it passes through all other vertices of the graph exactly one time. Just like here is the circuit A, B, D, Z, E, H, F, C, A. And second example is it also so that Hamilton circuit because their starting point and ending point is same. Like here is the graph circuit is A, B, C, E, D, A. Now moving on the examples of Hamilton path. Next slide. First example is graph A. It shows that Hamilton path because it contains each vertex of graph is exactly once, like A, B, C, E, D, and also C, B, A, D. These two are the Hamilton path. Second graph is also showed at Hamilton path. It is also the sorted Hamilton path like A, B, C, F, H, E, G, D, and G, D, E, H, F, C, B, A. These two are the Hamilton path. Next slide. Now we move on finding Hamilton circuit. Condition for the existence of Hamilton circuit is there is a simple way to determine whether a graph has a Hamilton circuit or path. At first, it might seem that there should be an easy way to determine this because there is a simple way to answer the similar question of whether a graph has a Euler circuit. Surprisingly, there are no known that given sufficient condition for the existence of Hamilton circuit. Next slide. Now, properties to look for. Uh, However, also certain properties can be used to show that a graph is a no Hamilton circuit. For example, instance a graph with a vertex of degree 1 cannot have a Hamilton circuit, and because in a Hamilton circuit, each vertex is incident with two edges in the circuit. Moreover, if a vertex in the graph has degree 2, then both edges that are incident with this vertex must be part of any Hamilton circuit. Also note that when a Hamilton circuit is being constructed, this circuit has passed through a vertex. Then all remaining edges incident with this vertex other than the two used in the circuit can be removed from consideration. Furthermore, a Hamilton circuit cannot contain a smaller circuit within it. Next slide. Here, here are the sufficient conditions. Although no useful, necessary, and sufficient condition for the existence of Hamilton circuit are known, quite a few sufficient conditions have been found. We state two of the most important sufficient condition here. Se- Next slide. First one is Dirac theorem. It states that if G is a simple graph with n vertices, with n is greater than equal to 3, such that the degree of every vertex in G is at least n by 2, then G has a Hamilton circuit. And second theorem is Or's theorem. It states that if G is a simple graph with n vertices, with n is greater than equal to 3, such that degree of U plus degree of V greater than equal to n, and for every pair of non-existent vertex U and V in G, then G has Hamilton circuit. Both of Or's theorem and Dirac theorem provide sufficient condition for a connected simple graph to have a Hamilton circuit. However, these theorems do not provide necessary condition for the existence of Hamilton circuit. For example, the graph C5 has a Hamilton circuit but does not satisfy the hypothesis of either Or's theorem or Dirac theorem. That's all from my side.
Now let's move towards finding Hamilton circuit with the help of some questions. As we all know that it is defined as a cycle that passes to all the vertices of graph exactly once, except the starting and ending vertices, that is same vertex. Here we have the question in which this is a graph where Hamilton path is A to G to F, E, C, D, B, and A, in which we can see that we are starting from the vertex A and ending at the same. Next slide. Here we have some graphs in which in the first graph we can travel from A to B, C, D, E, and A. Here we can see that we cannot traverse F, so this is not a Hamilton circuit. In the second question, this is also not a Hamilton circuit. The third one, here the path is like A to E, H, D, C, G, F, B, and A. Similarly, D has also the same path. This is also a Hamilton circuit. The next graph is not a Hamilton circuit. And F, here we can see that we are starting from A and ending at the same. So this is also a Hamilton circuit. Next slide, please. Now let's find the number of unique Hamilton circuits in a graph. As we have seen that can just simply count the we can just simply see the path of the Hamilton circuit. But to check that what are the total number of Hamilton circuit in the graph, here's the formula n minus 1 factorial. For example, if a graph has 5 vertices, then the factorial will be the total number of vertices like 5 minus 1 factorial, which is 4 factorial equals to 24. Here we have some examples that how many unique Hamilton circuits are there in a complete graph with the following number of vertices, 4 and 9. Next slide. Now let's move towards the applications of Hamilton circuit. A Hamilton circuit or path may be used to solve practical problems that requires visiting vertices such as road intersections, pipeline crossings, communication network nodes. It is also some real application in such diverse field as computer graphics, electronic circuit design, mapping, and operational research. We can also solve traveling salesman problems using Hamilton circuits. Next slide. Here we have the summary of the total PPT about Hamilton circuit and Hamilton path, in which repeated visits to a given node is not allowed, repeated travels of a given edge is not allowed, omitted nodes are not allowed, and omitted edges are allowed. Next slide. So this was all about our presentation on Hamilton circuits and Hamilton paths. Thank you for listening us so patiently.
Is there any question from the student side? No question. Can anyone tell me in your group, from your group, like you have mentioned the problem, traveling sales problem. Can you define what is this problem? What kind of application is this? Anshika, Anam or Nasreen?
Yes, ma'am. Ma'am, this
Huh.
problem, in this problem, we have the list of the cities and distances between each pair of city, and we have to find that what is the shortest possible route that visits each city exactly once and return to the origin city.
Okay, you have given the one formula for finding the number of circuits based on the number of nodes. So you have given that n minus 1 factorial. That is only for the complete graph. Fine.
Yes, ma'am.
Yes, ma'am.
The number of circuit will be n minus 1 factorial. Can it will be applicable to the non-complete graph? Complete graph में we can find the number of circuit by using n minus 1 factorial. What does if we don't have the complete graph? Then what can be the number of Hamilton circuits?
Ma'am, if the graph is not complete, then there will be no Hamilton circuit in the graph.
Is it a condition?
Yes, ma'am. The graph should be
For
simple and
for
complete
having
and
the
connected
Hamilton
for the
circuit.
Hamilton circuit.
Sorry, दोबारा बोलो.
Ma'am, the graph should be simple, complete, and connected to satisfy the condition of Hamilton circuit.
Okay, just one thing. Connected graph और complete graph को कैसे differentiate करोगे तुम?
Sorry, ma'am. Sorry, ma'am. Complete is not the necessary condition. Ma'am, I forgot. Ma'am, the graph should be simple and connected.
Simple and connected. So that's why I'm asking that you have mentioned that the for the complete graph, the number of cycle will be n minus 1 factorial. I'm saying if graph is not a complete graph, then what will be the number of Hamilton circuit or Hamilton path? आपने जो फॉर्मूला दिया n minus 1 factorial, that is for the complete graph as per your presentation. है ना? As per your presentation, so number of circuit will be n minus 1 factorial if it is a complete graph. You have given me this formula. If I'm not mistaken, Anshika, Anam and Nasreen.
Yes, ma'am.
So if I'm not having the complete graph, then what is the possibility of having the number of circuits? Or is it possible if I'm not having the complete graph, there is a possibility of having the Hamilton circuit or Hamilton
Yes,
paths?
ma'am. Yes, ma'am. There is a possibility.
Okay, fine. Take it. Okay. Any other group?
Okay, thank you, ma'am.
Thank you. Any other group? It was a nice efforts. आप लोगों ने पूरा हिस्ट्री वगैरह सब उसका निकाला, सब एग्जांपल्स आपने दिए हैं. It was a nice. Any other group
Thank
who
you, ma'am.
wants to present
Thank you,
the
ma'am.
presentation? And the important thing that you have prepared in a very short notice actually.
Yes, ma'am.
Hmm. So any other student? कमॉन बेटा, इतने मुश्किल टॉपिक नहीं है कि आपको कल सुबह शायद मैंने दिया था तो आपको नहीं प्रिपेयर हो पाता, आपको 5 से 7 मिनट की पीपीटी आपको तैयार करनी थी.
Ma'am, if my PC will be charged, then can I give my presentation in lab?
I can share the screen if you can send me a presentation, then you can present.
Which is like बहुत like पूरी battery dead है like.
No, I'm saying कि I can share your, I can show the presentation, I can share the screen and you can present the presentation.
Okay, ma'am.
आप फोन से तो कनेक्ट है ना?
मैम बट मैंने उसे मतलब फोन में जो भी मेरे डॉक्यूमेंट है उसे मैंने लाइक अभी मेल नहीं किया है, सो आई डोंट हैव दैट पीपीटी इन माय फोन राइट नाउ.
ओके, तो हो ही नहीं सकता जब तक मेरे पास आएगी नहीं. एनी अदर? If I'll say कि some weightage can be given to the students who is presenting today. Because you all of you are now presenting on your comfortable zone. Anshika and Nasreen has tried, at least they have put an efforts to present the screen, and other students will be presenting as per their comfortable zone. Okay, fine. If nothing is there or no one is there ready to present the screen. Okay, on Monday onwards, you have to complete your presentation in maximum 7 minutes. So Tuesday I'm having the class at 10 o'clock, but I will start at the 9 o'clock. So we all are having the presentation from 9 to 11 on Tuesday. And try to join the class within 5 minutes. Means I will generate the link at 8:55. So all of you can try to connect as early as possible so that we can start the presentation and we can finish the presentation on time. So don't be late on that day. So maximum 5 minutes.